Okay, we're going to finish the rest of the reactions from chapter 8, and obviously there's a lot of reactions in this chapter, but all the ones that we've done so far followed the same mechanistic family of electrophilic addition reactions. So now we're going to shift gears a little bit and look at other reactions without talking so much about the mechanistic details, although there'll be a few bits of information about mechanisms just to kind of help you understand why these things happen. And I'm going to start with the complementary hydration reaction that kind of fits with the last couple of hydration reactions that we saw. And this is called hydroboration. And borane is a molecule that you may have seen in general chemistry, and we used it earlier this semester as an example of an atom that doesn't have its full complement of 8 electrons in its outer shell when it's made all the bonds that it can make in the traditional way. So the boron in borane is a strong Lewis acid because it has an empty orbital, and it's sp2 hybridized, and so it can accept a pair of electrons, and actually it's not able to exist as plain borane in a by itself. It actually makes a dimer, which is kind of interesting, or it forms a complex in solutions of ethers. The ethers, unshared pair of electrons on the oxygen, act as the Lewis base to help stabilize the empty shell on the empty orbital on the boron. So in any event, no matter how it exists in solution, still the boron will act as a Lewis acid and attract the electrons from the pi cloud of an alkene as the Lewis base. And that's how things get started. And we're going to see the reaction on the next slide, but I wanted to say a couple more things about this. The borane has 3 hydrogens associated with each boron. And actually all 3 of those hydrogens will be able to be donated to 3 different alkene molecules. And it will do it in such a way that the hydrogen and the boron come onto the same side of the alkene. Now, ultimately, you may realize that we don't want the boron on the carbon, and so eventually we have to get it off. And the way that these hydrogens are delivered to the alkene, probably due to steric conditions, which is crowding, is going to do it in such a way as to put the hydrogen on the more substituted carbon because it's less bulky than the boron. And even though boron itself is not very crowded, remember we're going to do this 3 times, and so the steric consideration steers the boron to the more substituted carbon, to the less substituted carbon because it's less crowded. And so we say that this reaction is anti-Markovnikov or non-Markovnikov orientation. And so eventually we have to get rid of the boron, and we'll replace it by an OH group when we do the second reaction. And it also will stay on the same side. And because the hydrogen and the OH end up on the same side of the molecule, we call that syn addition. And so the reaction is also regiospecific. So let's look at an example. So here's a picture of the boron complex forming with this example alkene. And so you see the boron is on the less crowded carbon, the hydrogen is on the more crowded carbon. And so this complex forms, and it's kind of a little pericyclic step that this bond breaks, and this bond forms, and this bond breaks, and this bond forms, and that's how you get to this structure, and kind of all at once. And one reason we think that those bonds form all at once or break all at the same time in what we call a concerted reaction, because these 2 things are on the same side. And so the first part of the reaction is we put the alkene and the borane together. We get to this thing, and then we add hydrogen peroxide in an aqueous basic solution, and it oxidizes the boron off and replaces it with an OH. Now this is just showing 1-to-1 ratio here, but actually this will keep going, and actually another alkene will react with this guy, and then the product of that will react with another alkene, and so that's why it gets more and more crowded as you put more and more of this stuff around that little boron. So this is my generic way of writing this. So we're going to balance this equation this time. So we're going to have 3 of these alkenes, and again I have 2 different degrees of carbon, so we can make note of what's important. We're going to react it first with borane in an ether solvent, and then we're going to follow that product, whatever we get out of there. We're not going to isolate, but we're just going to keep right on going to the second reaction where we put in the aqueous basic hydrogen peroxide, and that will replace the boron with the OH groups, and so we'll get the exact opposite of what we would have gotten if we would have done hydration with either the sulfuric acid in the industrial process or the oxymercuration. We have anti-Markovnikov orientation, so the hydrogen ends up on the more substituted carbon and the OH on the less substituted carbon. Here's what I was talking about when you actually do this reaction 3 times on one boron. You get all 3 of those chunks of carbon around the one boron, and that crowding is what steers it to go to the less substituted carbon. And of course in this case it's the same degree, so you can't really tell that in this particular example. Anyway, that's one picture. So we haven't drawn all the pictures of all those intermediates, but just so you appreciate why it gets crowded. And here's another example, pretty much the same thing we saw earlier. The cycloalkene puts, this is the more substituted carbon, this is the less substituted carbon, so I'm going to put the hydrogen here and the boron here. And again, we're going through this 3 times. This one's not balanced. And then we oxidize this off and replace it with the OH from the peroxide. And we get this product, which is, again, the opposite of what you would have gotten if you would have done either of those other hydration reactions. So now we have control. So here's an example of an alkene with 2 different degrees of carbon. So this carbon is tertiary, this carbon is secondary. And so if we do the kinds of hydrations we talked about when we were doing electrophilic addition reactions, the hydrogen would go to the less substituted carbon. Remember Markovnikov's rule. And so there it is right here in blue. And the OH goes to the more substituted carbon, and here it is in pink. Now remember, this one went with the mercury first, and then it gets replaced with a hydride from the sodium borohydride. So anyway, there's our alcohol product if we do the this kind of hydration reaction. In a complementary reaction then, if we do the hydroboration, we put the boron onto the less crowded carbon, and the hydrogen from the borane goes to the more substituted carbon. Remember, that was the steric reason. And then ultimately the boron gets replaced with the hydroxide with an OH group from the peroxide, and so we get a complementary alcohol. So now we can choose which one do we need, which one do we want to make. We can get either one depending on which set of conditions we use. We like to be in control. We like to have that power to pick and choose. So this is a good thing. So let's practice again. So if we start out with this alkene, the first thing we need to recognize is that these are 2 different degrees of carbon. And once you have 2 different degrees of carbon in your alkene, then you can choose different conditions and pick which carbon is going to get the OH. So in order to do this, and remember, if we're going to do this kind of reaction, this would give the same result. These conditions are going to give you Markovnikov orientation. So the degree of the carbon is tertiary, the degree of the carbon is secondary. So in Markovnikov orientation, you get the hydrogen on the less substituted carbon and the OH on the more substituted carbon. So I've numbered these carbons so that you can see that carbon number 4 is going to be the one that gets the hydrogen, and carbon number 2 is going to get the OH. So there's that product. Whereas if we do the anti-Markovnikov or non-Markovnikov orientation, the hydrogen is going to go to the more substituted carbon, which is going to be the one I've numbered as number 2 here, and number 4 is going to get the OH. So we can get either one of those products specifically. And then, of course, we can go back and ask the question, if you were trying to make these alcohols from an alkene, is this the only starting material you could have used to make this molecule? And how do you analyze that? Remember, if you think about it that way, then this carbon that has the OH on it could have been part of a double bond. One choice is this one here, but you could have had the double bond inside the ring. Now, it wouldn't matter whether it was here or here, that would be the same difference. And so here's a picture of that. And so then the next question is, would this also, with this set of conditions, make this molecule, or would we need a different set of conditions? So we again look at the degrees of the carbon. The tertiary carbon is going to get the OH if you're using Markovnikov orientation type electrophilic condition reactions. So this one would work just fine with these same conditions. And so here's an example of either this set of conditions or this set of conditions would work. Now let's talk about this one. If we wanted to make this from an alkene, again, we look here, we could have either had the double bond here, which is what we have here, or we could have had the double bond out here. So let's draw a picture of that. So then the question is, if you want this alcohol, do you use these same conditions or different conditions? So we need to know what the degrees of the carbon are. So this one is primary and this one is secondary. So if you use this set of conditions, which carbon would get the OH? It would be the less substituted carbon. So what does that mean? That means we have to use these conditions to get this alcohol from this alkene. So that would be the choice there. So in any event, we have all sorts of different ways we can get to whichever of these alcohols we want just by choosing which set of conditions we use based on this orientation and control with these different sets of conditions. Alright, so let's shift gears now and talk about something else. We're going to talk about the reduction of alkenes with hydrogenation over a catalyst. And the nature of the catalyst is something we need to know. It's going to be a transition metal. Now I've got a little bit of the periodic table here, and it turns out that these guys right here, the nickel, palladium, and platinum, are the common catalysts that are used for these kinds of reactions. Usually in the book they'll use either platinum or palladium, and the platinum in the form of platinum oxide or palladium on carbon. Now the way these things are made, the platinum is a precious element. It's pretty expensive. So by making it into its oxide, it still works, but it means that you've added a lot of mass so you can actually weigh out and be able to see how much you're getting. Or the same thing with the palladium. It's pretty expensive, but if you disperse it onto some carbon in the form of graphite, then again you've got a powder that you can actually weigh out enough, even though you only need a catalytic amount of this to be able to see it. We're just going to suspend it onto something else or make it into a different molecule so we have more mass for weighing and seeing what we're doing. And of course industrially they have other kinds of catalysts that they can use. You will probably not see too many examples of nickel at this point in the book, but it works just as well in a lot of situations. It's just a little bit milder catalyst, and we will see it sometimes later in the book, so it's important to recognize that it's kind of this little family right here all works. And so then you have a three-phase system. We're going to have this solid catalyst, we're going to have a solution of the alkene, and we're going to have the hydrogen gas. So that's a three-phase system. So in order to get all these guys to come into contact with each other, you usually have to stir it up pretty vigorously. And what we need is for the hydrogen to stick onto the surface of the catalyst. And people pretty much don't bother to balance the equation, or you don't try to measure out how much hydrogen you're going to pass into this solution, because you're not going to capture every hydrogen molecule, so you always use excess gaseous hydrogen when you do these kinds of reactions. And so if you have multiple alkenes in a molecule, then all of them are going to get hydrogenated, because you're just going to have to pass in excess hydrogen gas. And the other thing that we need to know is that this hydrogen is going to get stuck onto the surface of this catalyst, and so ultimately both of those hydrogens are going to come onto the same side of the alkene, and so we're going to again observe what we call syn addition, or same side. And so this reaction is also regiospecific, because we can imagine that you could have put the hydrogens on either side, and admittedly in this drawing you can't really tell, because once they stop being pink, you can't tell which one came from the hydrogen molecules and which one was already there. But we'll see some examples where you really can tell. And here's some drawings about this process. That here's the surface of the catalyst, and the hydrogen coming down and getting stuck onto the surface, and then the alkene coming and getting both of those hydrogens on the same side and then going away as an alkane. And we talked about those kinds of reactions when we talked about looking at the relative stability of alkenes and measuring the heats of hydrogenation. This is the reaction that we were talking about then. So here's an example of an alkene where we can actually see that these things are going to come on the same side. So here's our platinum oxide catalyst. This is acetic acid, is just also acting as the solvent, and hydrogen molecules, and again they've made these guys pink so you can see them kind of pop out of here, and they're on the same side, which pushes the methyls onto the other side. And so you get controlled addition here, same side syn addition, and you can really tell in this molecule. Here's another example. This is a bicyclic compound, and so all this stuff up here is going to prevent this alkene from approaching the catalyst surface with this top side. Is going to have to be out of the way. So it's going to get both of its hydrogens on the bottom, and you won't see any of this. But again, this is proof that there's a control in how this molecule gets its hydrogens. There's no free rotation, even though here it looks like you've got one hydrogen starting to get on there and this one hasn't gotten on there yet. It's not free to rotate and float around and then come back and get the other hydrogen. They really do come in at on the same side. And here's another example. In this case, you really can't tell that they're coming in on the same side, but all we need to do is make this into an alkane. So there's our product. And we're going to notice also that even though a ring is a point of unsaturation, this ring and that ring, those are points of unsaturation, none of those things are affected by catalytic hydrogenation. And we're going to see that there are some other kinds of unsaturated groups that are not affected either by these reduction conditions. But the main thing you need to know right now is that rings do not get affected by catalytic hydrogenation. Okay, so now for another reaction. We're going to talk about what's called epoxidation. This is a process of making a little three-membered ring that's got an oxygen as one of the elements of the ring. So that's generically called an epoxide. And a peroxy bond, like hydrogen peroxide, is an oxygen-oxygen bond, and the oxygen in an oxygen-oxygen bond is in a different oxidation state. Normally, oxygen likes to either be elemental as 0 or -2 is its most common oxidation state. But in a peroxide, it's -1. So obviously, it's not very happy. So any kind of peroxide is pretty reactive. And we talked about peroxides earlier when we mentioned radical reactions. Well, this molecule, if there weren't this extra oxygen here, would be a carboxylic acid. But with the extra oxygen, it's called a peroxy acid. And here's the short, inline text version of that. So if it were a carboxylic acid, there would just be 2 oxygens. So with the third oxygen, we recognize that it's a peroxy acid. And it will deliver that extra oxygen to the double bond. Now they've got some little arrows in here showing this. We don't really need to worry so much about the mechanism, but we just know that we're kind of inserting this oxygen between these 2 carbons and making this epoxide and frees up the carboxylic acid. Industrially, they don't use the peroxy acids. They use oxygen and air and a catalyst. But the next obvious question is, why do we want to do that? And if you have the epoxide made from ethylene, it's called ethylene oxide, and it's very useful as a commodity chemical. And if you've been on a vessel trip over to Texas City, one of the things we point out over there is the bunker where the ethylene oxide is stored, because it's a very reactive molecule and pretty hazardous. And we'll talk some more about the epoxides in chapter 18. We've got a little bit more about them in this chapter, but they're a type of ether, and so most of that information about ethers is in chapter 18. Something else I want to say about this. I've written it generically as R, and they're using an R right here. In McMurray's textbook, he has, over the years of, we're on the 8th edition, over the years of various editions, used different examples of peroxy acids and keeping up with the literature. And people in laboratory situations for trying to make these epoxides have tried different things and switched from one to another, partly for safety reasons, partly because the side products might be carcinogenic. For whatever reason, the keeping up with what's current in the literature has caused McMurray to make a lot of changes as you go through the different editions of the book. And so I decided to just always write this molecule as RCO3H and not really struggle with which particular peroxy acid is the one that's in favor in the literature, just to keep it from being confusing. So here's an example of one of the ones that's popular. It has been popular in the past. It's popular again. And this is called metachloroperoxy benzoic acid. And so we haven't talked about aromatic nomenclature or anything like that, but they abbreviate it as MCPBA. So in the first couple editions of McMurray, he used MCPBA all the time. And like I said, it just trying to keep up with which one is popular is really kind of silly, since they've changed so much. All you need to know is that we're going to stick this extra oxygen in between these 2 carbons and make the epoxide. So there's a picture of that. And the acid is the side product. So I'm going to use this terminology, the peroxy acid, for that. And part of the reason that there were so many changes is because I mentioned safety. These things can be spontaneously explosive, and so you have to be careful with them. You can't use that on a large scale, and so people are looking for different ways to do this. And one thing you can do is use the halohydrin reaction and then go from there. So this is a reaction that we saw in the other section of material and electrophilic addition reactions. Remember that the halogen added to the less substituted carbon and then forced the water to come on the other side. Now these both have the same degree of carbon, so it doesn't matter. The chlorine is going to be on one, the OH is going to be on the other, but they're going to be on opposite sides. So the OH is up, the chlorine is down in this structure. And then if you take that halohydrin product, you can react that with a base like sodium hydroxide, and it will pick off this, it'll do an acid-base reaction here because of the nearby chlorine that's making this a little bit more acidic, and so it will close up this ring and make the epoxide that way. So we're going to talk about the mechanism of that and more details on that in chapter 11 and again a little bit in chapter 18. But for now, it's just an alternative way to get to the epoxide. It's first the halohydrin and then some sodium hydroxide, and you can make an epoxide that way. It helps that the OH and the chlorine are on opposite sides. That's actually a part of why this works. So here's again the sort of the generic case where we take some alkene, we do whichever epoxidation route we want to use, and we make our epoxide. And so one reason we're interested in that in this chapter is that we can open up that epoxide with some aqueous acid and make a diol. And you notice that these two OHs are on opposite sides. Now these are both alcohol groups, and so the sort of short version of that is diol. OL is for alcohol. So it's a 1, 2. And again, the numbers here don't necessarily refer to the chain numbers that you would use for nomenclature purposes. It's really, they're on adjacent carbons. And they're on opposite sides or anti to each other or trans to each other. So again, why that is a mechanistic detail we'll learn more about later, but it's shown in this chapter because it's another reaction that partners with something else in this chapter, which we're going to talk about now, called hydroxylation. So again, we go back to the periodic table. In that same section of the periodic table, we've got osmium down here, and osmium is a fairly rare element, but it's able to take a +8 oxidation state. Anytime you have an element that comes from the transition elements bonded with a bunch of oxygen, it's going to be in a high oxidation state, so it's going to cause some kind of an oxidation. And we're going to use it here in catalytic amounts and actually recycle it. And there's a couple different ways that that's shown in the book. This is one way, and there's another way that this is shown in the book. But basically, you don't ultimately have to have a 1-to-1 ratio if you do this right, because of the expense and also it's toxic. But we're just going to write it like this. And this osmium is going to deliver the two oxygens and make this bond on the same side. So both of the oxygens are coming on the same side. And then when we oxidize this part off, we're going to reduce this guy off with this sodium bisulfite in aqueous solution in this example. The two OHs are going to be left on the same side. Now that partners back with this guy where the two OHs were on opposite sides. So this guy is going to be a syn-diol or cis-diol. So it complements that other reaction. And so here again we're going to practice with filling in the reagents so we get the right set of conditions to get the right diol. So we need to look at this product, and you see the two OHs are on opposite sides in this molecule, whereas the two OHs are both on the same side in this product. So we know, we just talked about it, if we want the two OHs on the same side, that's going to be the osmium tetroxide route, whereas if we want them on opposite sides, we're going to open an epoxide. So we can make this one directly from the alkene. Now, I mentioned that there was another way to recycle this, and that's with this NMO. That's the other way that the book shows you for recycling this catalyst. So either the osmium tetroxide an NMO or the osmium tetroxide followed by sodium bisulfite, you get the syn diol directly from the alkene. If you want the anti-diol, we have to go through the epoxide, and so we can do that with the epoxidation, and then we have to open that with some aqueous acid. So that's how we get to here. Or you could write it like this. We could say reaction number 1, do the epoxidation, reaction number 2, the aqueous acid. So here we're just showing the product of the first reaction and then the next set of conditions. Okay, so all of those things that we've been showing have only broken the pi bond. And that included the electrophilic addition reactions earlier in the chapter, and the ones that we've just seen, the hydrogenation and making the epoxides and all those things only broke the pi bond. And we did not ever disturb the carbon-carbon single bond, the sigma bond between the two carbons of the alkene. And so we're going to look at now a couple of new reactions that will break both bonds between the carbons of the alkene. And what that means is that if the alkene is in a chain, you're going to get two separate molecules. Whereas if the alkene is in a ring, it will just open the ring. So we'll see examples of both so you can kind of get an idea about what we're talking about there. One of the things we're going to use is ozone. And ozone is an allotrope of oxygen. And what that means is that it's an alternative elemental form. So ozone is found in the atmosphere. It's what makes the sky blue because it interacts with the gamma rays and gets into an excited state, and that's why it looks blue in the sky. It's also bad if it's near the ground because it's a component of photochemical smog, and then we don't want it near the ground. And when you say you smell lightning, what you're really smelling is ozone. In fact, that's how you make ozone in a lab, is you pass oxygen into a chamber where you direct an electrical current through this chamber like lightning bolts, and in the presence of that electrical discharge, you turn the oxygen O2 molecules into oxygen O3 ozone molecules. And then you take that material and you pass it on into the presence, bubble it into a solution with an alkene. And so that initially makes a molecule that's called a molozonide. So one end of the ozone gets attached to one of the carbons, and the other end of the ozone gets attached to the other end of the carbon. So this is the molozonide, which is really unstable. I mean, you know, we talked about the peroxide and oxygen. Well, this was even worse. And so this will spontaneously rearrange. So when you get to the molozonide, you know, you've only broken the pi bond. But now when this guy rearranges, you break the sigma bond, and so one of those oxygens moves over and breaks that other bond apart. And then we actually do a reduction, typically with zinc in an aqueous acid solution, and wherever this carbon-carbon double bond is, both of those carbons become carbonyls, and the zinc gets oxidized. And so the carbons are actually reduced in going from here to here, but the zinc is oxidized. Alright, so both ends become carbonyls, and carbonyls are part of a bunch of different functional groups, so just knowing that they become parts of functional groups, we don't yet know what we formed. We have to look to see what else is on those carbons. And so our possibilities are aldehydes and ketones. And aldehydes are also sensitive to oxidation, but that last step of this ozonolysis was actually reduction, so we can keep any aldehydes that we get. So let's look at this example. This alkene is part of a ring, but the double bond is what's called exocyclic. It goes from a ring carbon to an external carbon. So this is not going to break open the ring. Remember, I started out saying that if it was inside of a ring, it would open the ring. If it's outside of the ring, it doesn't bother the ring. And these are carbons, all carbons attached to the double bond. So the product, when we make both of these carbons into carbonyls, is that we're going to make two different ketones. Now you notice that they've turned this, kind of turned it from the way it was oriented in there. But we get two ketones out of that. And so here's the short version of writing this down. First ozone and then the zinc in aqueous acid solution. Here's an example where the double bond is inside of the ring. So if we react that with ozone, and I've numbered the carbons to kind of help you keep track of who goes where, then this carbon right here, number 1 in this labeling, when that becomes a carbonyl, 6 and 7 are attached to that, and so that carbon is going to become a ketone. This carbon is attached to a hydrogen, which is implied here, and so when it becomes a carbonyl, it's going to become an aldehyde. Now, I've drawn this kind of like we just split this apart so you can kind of see exactly where the double bond used to be between 1 and 2. And this double bond is what we call endocyclic. It's inside of the ring, and so it opened up that ring. And so carbon number 2 becomes an aldehyde. We get to keep that hydrogen if we're doing ozonolysis. When you see this product, the way the book would do it, they might write it out in a chain, but you see the numbered carbons, how when they open up, where they came from. It helps a lot if you number the carbons so you can make sure that you don't make any mistakes when you write it out. Here's another example in the book, and I wasn't particularly fond of this particular example because they throw in this other functional group, but what they're trying to show you is a natural product. This is a molecule that's found in nature, an ester of one of the fatty acids, and it turns out that this set of conditions doesn't bother the ester, and so we're just going to break open this chain right here, right where the double bond is. Both of these two carbons have hydrogens on them. Remember, we call those vinyl hydrogens. And so wherever these vinyl hydrogens are, we get to keep those. And so both of these carbons are going to become aldehydes in this example. So with this set of conditions, we can make aldehydes and or ketones depending on what was originally attached to those two carbons. On the other hand, if we use permanganate, potassium permanganate is another example of an transition element bonded to a bunch of oxygen. And so if you go back to general chemistry and think about it, if oxygen is -2 and potassium is an alkali metal, can only be +1, well then the manganese has to be what? +7. So it's another guy that can be a good oxidizing agent. And it's dark purple, and a lot of times when you see it in aqueous solution, it's purple, and it oxidizes a lot of different things, and this is just the first time that we've run into it. But it will oxidize things pretty easily, and I mentioned that aldehydes are pretty sensitive to oxidation, and so if you make any aldehydes as products, they keep right on going. They get further oxidized to carboxylic acids. So let's go back to this example. We had here a double bond, and this carbon right here is attached to two different carbons. So that guy, when this becomes a carbonyl, is going to become a ketone. But there's a vinyl hydrogen here, which would theoretically go to an aldehyde, and here's that picture of that. But I've drawn it in brackets because we can't stop it from going on. In the presence of permanganate, it's going to keep right on going and making this carboxylic acid. So wherever the vinyl hydrogen are in the presence of permanganate, you go right on to a carboxylic acid. And we use this bracket sometimes. You'll see it at in other situations. We always mean that we don't get to keep that. And again, I've numbered the carbons here so you can kind of keep track of who ends up where. So carbon 3, 5, and 6 end up in the carboxylic acid, and 1, 2, and 4 end up in the ketone. So here's another example. Now what happens here is this is a terminal alkene. And so you have a CH2, which is like 2 vinyl hydrogens. And so what happens is that this one is a vinyl hydrogen, that becomes a carboxylic acid, but this guy over here becomes CO2. So here's a question, how did that happen? Well, let's see. If you went through ozonolysis, you would have made the aldehyde okay, and formaldehyde would be the other product. But you notice that that's kind of like what I would call a double whammy aldehyde. Wherever there are any kind of aldehyde hydrogen, we're going to replace that with an OH with this further oxidation if we're doing this route. So if we put that guy in brackets because we can't keep it, in permanganate, it's going to go to this. Does anybody know what that is? What if we write it in an equilibrium of aqueous solution? You see, that's the CO2. In Gen Chem, you might have written it as H2CO3, and then maybe you would have recognized that's just carbonic acid. Okay, so it will have the CO2 in solution, but it will bubble out of your soda or out of this solution as well. So any terminal alkene is going to have CO2 as one of the products if you use permanganate. And if it's a terminal alkene with ozonolysis, you'll make formaldehyde as one of your products. Now, we talked a couple of slides ago about making syn-diols from alkenes. And so here's a reaction where you can take a syn-diol with per-iotic acid in aqueous solution, and it will also complex with that diol. Now this is iodine in a high oxidation state because it's bonded to a bunch of oxygen. So it's a good oxidizing agent as well. And it will give you exactly the same products that you would have made from ozonolysis. Now, one question you might ask is, well, where did this come from? And it actually is used because carbohydrate molecules have situations like this, where you have a bunch of OHs on a chain of carbons, and you can kind of check and see how many of them are on the same side by using this kind of reaction. So that's where the real utility of this came from, is not so much from starting with alkenes, but you can start with alkenes, but also because of the carbohydrate studies. So same products as with ozonolysis. Here's another example. So we can just break this apart. So if you had this diol, then it's like it was a double bond here, and this also breaks that apart. Once you leave this intermediate, it's going to break that apart, and both of these carbons are going to become carbonyls, and so you make 2 molecules of cyclopentanone. Alright, so let's think about working backwards. Now, we've been working backwards when we talked about hydrohalogenation and dehydrohalogenation. We've looked at making alcohols and by hydration or dehydration. We went back and forth. So let's do that again. Alkene oxidation was historically used, and sometimes still is, to help determine what the original product was. You would oxidize the alkene, look at the little pieces that you get out, and then from that figure out what the original molecule was. And so suppose you have this information. You have ozonolysis followed by the zinc and the aqueous acetic acid, and you get these 2 products. And you want to know, what was the original alkene? I mean, you see this, you see that, you think, okay, the original starting material was an alkene. Well, remember what we said. The carbon that was the double bond carbon becomes a carbonyl. So that means that this was part of the double bond, and this was part of the double bond. So basically, we need to put those 2 carbons together with a double bond, and that must be the original molecule. So here we've kind of drawn those 2 things and sort of suck those out of the way and just put it together. So in the book, at the problems at the end of the chapters, there are these problems we call roadmap problems. And they start out like this, and we did one of these in class in kind of a different way. But let's see if we have this. It says compound A has the formula C10H16. So before you read any further, you can figure out how many points of unsaturation there are. And we also know that if you have any alkenes, you can do catalytic hydrogenation and turn alkenes into alkanes, but that won't affect rings. So, so let's start at the beginning. So from the first sentence, we can figure out how many points of unsaturation. So we compare C10H16 to the alkane formula C10H22. The difference of 6 means that there's 3 points of unsaturation. So that could be 3 rings, it could be 3 double bonds, or it could be a mixture of rings and double bonds. So then we read the next sentence. And so catalytic hydrogenation over palladium only reacts with 1 molar equivalent of hydrogen. What does that mean? It means that it only is going to change this formula by 1 pair of hydrogens. So we're going to go to C10H18. So again, if you go back to the alkane formula, the difference now is 4, so it still has 2 points of unsaturation. Now we already said that rings don't react with catalytic hydrogenation, so that tells you that these 2 points of unsaturation must be rings. So we go back up here, we say, well, we must have had 2 rings and 1 double bond in our original C10H16 compound A. So those 2 points of unsaturation are rings. So here's the equation again. The problem again. So let's see what the next sentence says. It says compound A also undergoes reaction with ozone, followed by zinc treatment to yield a symmetrical diketone, and here's its formula. What is a symmetrical diketone? Well, it's got 2 carbonyls. Alright, that's what the diketone means. And it's symmetrical. Alright, what else do we know? If we look at the formula, we can ignore the oxygen, again, compare it to the alkane. It still has 3 points of unsaturation, but because it's a diketone, we know that 2 of them are carbonyls. Now, we knew that compound A had 2 rings and 1 double bond. We've done this reaction, this ozonolysis, and we have now 2 carbonyls. We must still have 1 ring. So now we have to figure out the structure. So we originally had 2 rings and 1 double bond. Now we have 1 ring and 2 carbonyls. Where could the double bond have been in the original molecule with 2 rings? Well, you're going to have to work on that a little bit. We know that compound A had 2 rings and 1 double bond, and it must also be symmetrical because the product of this ozonolysis is symmetrical. So there had to be symmetry from the very beginning. And if you had 2 rings, to get symmetry, it would probably help if they were the same size rings. And the next question is the double bond endocyclic or exocyclic. You remember what that means. Is it internal to one or the other of the rings? Or is it outside of a ring? If it's inside of a ring, it's going to open the ring. If it's exocyclic, it's going to chop off whatever's sticking out off of it. In other words, if I had 2 rings, 2 separate rings connected by a double bond, then it would separate them from each other. And yet, when we do this ozonolysis, we only end up with one product, this compound B, and it still has a ring in it. So what is that telling you? It's telling you that the double bond has to have been endocyclic, but it has to have been between the two rings. So here's what it could be. You could have two rings the same size connected by a double bond, which when you do the ozonolysis will open up to make a symmetrical diketone. And when you do the hydrogenation, you still have your two rings, but you just get rid of that double bond. If you imagine that you had like a 5-member ring and a 7-member ring, then your ketone, your diketone would not be symmetrical. And if they were two rings connected by a double bond, we'd have made two products instead, two molecules, with one carbonyl instead of a dicarbonyl. All right, let's try that again. So here's another problem. It says compound A, C10H18 under O, and so we can stop right there and figure out how many points of unsaturation. So what do you know? We're going to compare that to the alkane formula. So this one has 2 points of unsaturation. Alright, so now we keep reading. It says it undergoes reaction with dilute sulfuric acid at 50 degrees to give 2 alkenes. Alright, so we need to figure out, from that tells us that this was an alcohol. This may look a little bit familiar to some of you. We know that these points of unsaturation could have been, various things, so we need more information to know for sure. So the reaction that we're talking about here tells us that we had to have had an alcohol, and compound A contains an oxygen, so it must be an alcohol. And since there are two different products here, it means that the alcohol can't have been symmetrical. Alright, so let's keep going. We know something now. It says the major alkene gives only cyclopentanone after ozone treatment. Alright, here's a picture of cyclopentanone. Alright, so how is it possible that we can only get one alkene, have an alkene and only get one product? Okay, if this is our product from one of these alkenes, how is it possible to only get one? Well, what it tells us is that we actually had two of these guys hooked together by a double bond. Okay, and so it must have been an exocyclic double bond hooked to another 5-membered ring. Okay, and then we have compound B, which is the product that we were looking at, but we can probably also figure out the other thing too. So compound A must be an alcohol where we had an OH on one of those. Okay, so here's the solution. So this is what compound B has to be in order to give us this product during ozonolysis. And so that means A must have been this when we do the dehydration reaction. So then the other question we get asked is, well, what is the other alkene going to look like from this dehydration reaction? It's going to put the double bond inside of the ring. So there's our other product. Alright, so let's shift gears one more time and let's look at a couple more reactions of alkenes. Back in chapter 1, at the end of the chapter, somewhere in there, we talked about carbenes. Carbenes are carbons that have 2 bonds, but they have 6 electrons. So clearly they're not happy, and they can exist as either sp2 or they can exist as sp. And the sp version is more stable because those 2 electrons are not paired, and these carbons don't have a formal charge, and here's one way you can make one. This is actually called an alpha elimination, because we're going to take chloroform, is the common name for trichloromethane, and we're going to put in a base, and this hydrogen is pretty acidic because of the electronegativity of all these guys, and that will at that moment leave behind a pair of electrons on the carbon. Now these chlorines are all pretty electronegative, and so they get pretty upset about that, and so one of these chlorines just takes off with the pair of electrons and leaves behind this carbon with, now it's lost this pair, so now it's only got 2 bonds, and yet it's still got this pair. So the initial product here is what's called a singlet carbene, because at this point it would be sp2. And we call this alpha elimination because both the hydrogen and this chlorine came off the same carbon to get to this carbene. And this is called a dichlorocarbene for fairly obvious reasons. Okay, so the carbene's not happy, and so it will react with an alkene. And this reaction is also concerted, which means it's like pericyclic. The bonds are going to form all at once and a cyclic fashion. And so here's the colored version. From here you get the carbon and the 2 chlorines that stay with it, and you insert that kind of like the epoxidation reaction, only this time the third member of the ring is going to be this carbon, and your side products are KCl and water. And here's another reaction. We're just going to put that extra carbon in here and make this dihalogenated cyclopropane ring. Alright, so there were these guys that were told that they wanted to work on this, kind of making these little 3-membered rings to make some agricultural products. And they worked for DuPont, and their names were Simmons and Smith. And they needed to make cyclopropane rings, but they didn't want the chlorines on there because they wanted to mimic pyrethrins, which are found in chrysanthemums and are able to be used as deterrents to predation by ants and other things. And so they wanted to make large quantities of pyrethrin type molecules, which, as it happens, contain cyclopropane rings, and they don't have these chlorines on. So they used kind of the same idea. They wanted to make something that acted like a carbene, that is, so that they can insert it into the double bond. So they wanted a 1-carbon molecule, and working with halogens seemed like a good idea. And so they found a way to make a species that acts like a carbene. So we're going to call it a carbenoid, but it's not really a free carbene. So here's what they did. They took diiodomethane and they reacted with zinc. This is called a zinc-copper couple. You could kind of think of it as a solution of zinc in copper. Now, when we think about metals, we don't really think about solutions so much. So it's called a zinc-copper couple. But you may realize that zinc is a more reactive metal than copper. That's why they use zinc anodes on the ship to help prevent it from corrosion. And so the copper keeps the zinc activated. And so it will essentially get oxidized as it gets into the middle of this molecule. And so this guy right here is going to act like a carbene. So they put in quotation marks because it's not really free. And so we can take the Simmons-Smith reaction, this combination with the diiodomethane and the zinc-copper couple with an alkene, and you can make a cyclopropane ring that is just a plain cyclopropane type ring with CH2s here instead of the chlorines. So here's another example. If you take this molecule and you put in this set of conditions, you're going to make a 3-membered ring out here. It doesn't matter whether you draw it up or whether you draw it down, but it's going to have the chlorines on it. Whereas if you do this set of conditions, you're going to make a 3-membered ring here, but it's just going to be a CH2 out there. So here's a picture of the first product Here's a picture of the other product. And again, it doesn't really matter whether you draw it up or down. It's just a CH2 as opposed to the carbon with the chlorines. If we had said that this was a trans molecule, because this is a concerted reaction, then the product would be trans. Here's a picture of that. Okay, so if this group and this group were on opposite sides, we would still have that. We would maintain that, and that's part of how we know that this is a concerted reaction. Alright, so there were a lot of reactions in this chapter, so you've got a lot of reagents to learn and what they do, and you should be able to start anywhere in an equation. Remember the math concept. A is the substrate, B is reaction conditions and with reagents, the molecules that are going to transform the substrate into the product. So if you know any two of those, then you should be able to figure out the third. And in terms of mechanisms, you need to know the electrophilic addition mechanism. You need to be able to write out the details, figure out who is the electrophile, draw the little arrows that show the alkene reacting with the electrophile, and then whatever the other piece is, the nucleophile in the second step comes back. You need to draw a reaction energy diagram for that. Remember, that's going to have the two hills. The first step is going to be the rate determining step. There's going to be a carbocation reaction intermediate. All of them look like that. And you need to be able to complete interconnected or related reactions and roadmap problems. There are examples all throughout here. And you need to keep track of which reactions are regioselective or stereochemically significant, so they make trans products or they make, anti-addition versus syn or cis type products, which things lead to racemic mixtures, and all of those kinds of details become important. And that's the end of this chapter.